streaming. All right. Yeah, so it doesn't, I don't think it's a good idea for classes. There we go. All right. 7 in the morning. Wow, that's brutal. Oh, is that calculus, right? Yeah. Alrighty. So I'm just positioning all the stuff to be at the right place and looking at the clock. We got about 5 more minutes. So what we'll do today is to finish up. Well, okay, we'll talk a little bit more about floating point numbers, and then on Thursday, we're gonna talk about the practice exam, which means next Thursday is exam one, and that's right on target because I said exam one will be in week 6, so it's about the right time for that. So if you look at the text channel, I have an attachment, which is an HTML document. That's the practice exam. I'm not going to talk about it today. We'll talk about this on Thursday. So you guys got about 2 days to look at this particular exam and just kind of think about how to answer those questions because, and I have to think about how to ask uh, questions in a different way. So I have my challenges too. Um, and then on Thursday, I'll talk about how to answer those questions. Some of those are not too difficult, and the first few probably can be a little bit challenging. So we'll talk about that on Thursday. All right, just looking at the time, we still got 3 more minutes or so. I'm not sure how many people are now online. I got some on Google Meet, and then on YouTube, we got about 4 people. All right. Oh, I can talk about, fall 2021. I was in a meeting earlier today, and the chancellor of our district was talking about plans to quote unquote reopen the campuses. And obviously, no one's going to know what's going to happen in fall 2021. And chances are we are not going to be 100% in the clear. So we might still be in red, orange, or yellow mode, which means, depending on which color we are in, some classes will be offered uh, on the ground and other classes will be online. For CIS, everything is going to be online. You can almost count on it 100%. I mean, there's a very, very, very slim chance that some of our classes may be on the ground in fall, but I think that chance is really slim. So my question to you guys is, do you guys prefer classes online or do you prefer classes to be on the ground again? Mm-hmm. Mm-hmm. That makes sense. Yeah, I think even if you they somebody did a study. There's a large space in Folsom Lake College that was supposedly that can house 100 people. If they take into consideration of social distancing, the occupancy will drop down to like 25. Um, that was not a lab situation. That was probably just a space, common space issue. Okay, I'm looking at some. I'm looking at the feedback in the text channel. So face to face, half and half. Yeah, it depends on the class too. With most classes, I personally prefer to teach, face to face, just so that I can see people frown and make faces to me. It's like I have no idea what you're talking about. Well, because if I can see those faces, I can stop and I go like, okay, well, I know you guys have questions. Go ahead and ask now. hmm Nathan makes a very good point. That's the that's the structure of conventional, on the ground classes. This is also why I specifically requested synchronous classes because then I have structure. Because if I don't have structures, trust me, I'll be the first one forgetting to go to a class to teach that class. I'm not sure about that, Caleb. I think with devices now, people can stay distracted 24/7. Just watch that Netflix documentary called Social Dilemma. So we got one person. David was the first one to say it like online. Yeah, I think the structure really is important. As much as I personally sometimes go like, oh, I wish I can be more flexible and use some other day or some other time to teach the class. I think it's really good to have that structure. Okay, yeah. Okay, so let's go ahead and get started. I'm still keeping an eye on the text channel, which is definitely one thing that can be very distracting, especially now that I'm using Discord. If you have other Discord servers that you belong to, you can definitely see all of those notifications while you're taking classes. So I can certainly tell I can certainly understand it can be distracting. And then we got something that really belong to the off-topic channel because that's the reason why I have the off-topic channel. Um, well, yes, but then I'm gonna focus on today's lecture. Um, if you go to the pinned area, there is um, the link to the YouTube for today's lecture, but there's also a document. That document is the actual exam from last semester. So it's the actual exam one from last semester. I'm not going to talk about it today. I want you guys to kind of spend the next 2 days or so to try to answer those questions, and then on Thursday I'll go over that particular exam, the so-called practice exam for this semester. Our actual exam is going to be next Thursday, so make sure you allocate the time slot for the lecture available for exam one next Thursday. All right. And then the scope of the exam, I know someone's going to ask that next, is going to exclude floating point numbers. So floating point numbers will not be in exam one. Exam one will have everything all the way up to and including binary number comparison and subtraction and all the flags, but it will exclude floating point number stuff. And we got a whole bunch of text. There will be no form now because this is a synchronous class, so we are all going to take the test from 5:30 to 6:50. So it's the same duration and the same time slot as the lecture. Um, Instead of a lab after the exam, I can use the lab time to talk about the key or the answer to the exam. So that can be the one use of the lab time. No, I do not believe in lockdown browsers, so I'm not going to use a lockdown browser. I do not plan to use Proctorial either. But you guys will see, I have my own way. Alright, so I'm still keeping an eye on the text channel, but at this point I am going to get started with floating point number representation. So the idea of floating point number representation has to do with we want to be able to represent values of a much larger range than just 0, 1, 2, all the way up to 4 billion something. Okay, that's the that's for 32-bit numbers, and then for 64-bit number, it is a larger value, but it is still kind of limited. Let me get started with my tablet. And I'm just starting it up now, so it takes a little bit of time to get back to the display. So give me a little bit of time to... Yes, I lost my mouse cursor again. That's interesting. It won't let me go beyond a certain point. Alright. Alright, there we go. And as usual, I need to start it twice. The first time it seems to sync, and then it doesn't actually get the job done right. And there we go. I thought I lost my stylus again, which happens a lot. But this time I actually did not lose it. And then I have to start it again. I have to find out what the bug is. What makes it, not work the first time. But the second time, it works okay. There we go. Nope, still not working. So I have to exit using its exit button. I cannot get rid of it from outside. Alright, there we go. And then let me put it in the area that you guys can view. There we go. Alright, so we want to compare the range of values that we can represent using just the integer representation. Signed versus unsigned is not so big of a deal because one would use the entire range for non-negative values. That's unsigned interpretation, and then for the signed interpretation, we just chop it half and half, right? Half of it would be non-negative values, and then the other half would be negative values. So with 64-bit numbers, okay, so with m equals to 64, the range of a value, if I use unsigned, is going to be from 0 to 2 to the power of 64 minus 1. The minus 1 has to do with 0 itself is a value already, and then there are only 2 to the power of 64 ways of arranging the zeros and ones. So this is it, okay? This is all we can do when we use the unsigned representation. And then most people will look at this value, especially this side here, and say, that's pretty big already. So why do we have an issue with it? Okay, it's already a huge value. Let's find out how big the value is, okay? So what we'll do is we're using a guesstimate way of looking at the magnitude of the value. And it's based on the fact that 10 to the power of 3 is close to 2 to the power of 10. This is a really kind of useful way for estimating when it comes to, okay, given this many bits, right, how many values do we have? So in this case, 2 to the power of 64 is exactly 2 to the power of 10. that to the power of 6 times 2 to the power of 4. Okay, now that's just coming from the exponents. Okay, I'm hoping you guys still remember these algebra concepts involving exponents. So now I can use approximation and say this is 10 to the power of 3 to the power of 6 times 2 to the power of 4. I keep flipping to the next page because it's interpreting my palm as swiping. Apparently I'm moving my palm when I'm writing. So this is now basically 10 to the power of 18 times 16. So you can look at this as 16 times 10 to the power of 18, which in scientific notation is 1.6 E19. Well, actually, I should not use superscript. It's 1.6 E19. In reality, it is 1.8 something. Okay, just because 2 to the power of 10 is really a little bit more than 10 to the power of 3, not by much. But when you raise that to the power of 6, it becomes kind of significant. So, so just imagine that you're writing the largest value is 1, 8, and then the whole thing has 19 digits to it. Okay, and you look at that number, you think, hey, this is a huge number. Well, not really. Okay, because a lot of stuff in physics involve values that are much larger than that, especially when you have to talk about the number of molecules within a certain amount of mass. I mean, those values are gigantic, right? I mean, this value that we're looking at here, that's not enough. And then we have another problem too. The other problem is we cannot represent anything between 0 and 1, excluding 0 and 1 themselves, obviously. So we cannot represent very small and tiny quantities, and those are really useful too in physics, because when we talk about the mass of a single proton, or the mass of a single photon, which is a whole lot smaller, then we are looking at a tiny value that cannot be represented using the unsigned integer representation. So how do we fix this problem? The way we fix this problem is the topic that we have started on last Thursday, and we're continuing that topic today, which is what we call the IEEE double precision floating point number representation, which is really a long way of saying scientific notation in base 2. Okay, it's really just scientific notation in base 2. So when we talk about scientific notation, this is usually what we have. These are the components. So we have a certain m, which is the Mantissa. I really should not have used m up here, but this is Mantissa. Okay, so you can look up Mantissa and find out what it is. So for our purposes, the Mantissa is a value between 1 and the base. Okay, but it's excluding the base itself. In base 10, it will be from 1 to 9.999999 something, depending on the precision of how many digits you can allocate to the Mantissa. So that's the Mantissa part. So the value is the Mantissa times some kind of base raised to some kind of exponent. That really is the whole concept of scientific notation. And obviously this works in base 10 too, right? The way it works in base 10 is if you have a value which is 1.23E45, this really is representing the value of 1.23 times 10 to the power of 65. So in this case, 1.23 is the Mantissa, 10 is our base, and then 45 is our exponent. Okay. Do we have any questions about the scientific notation in base 10, which is what we talked about on last Thursday? Alright, so there are no questions about this. Okay, cool. So now we talk about the scientific notation in base 2. You go like, okay, that has to be complicated. Nope, it's not complicated at all. Okay, so I can give you 1.011, And then this time I shouldn't use E, so I'll just spell out times 2, which is our base, raised to the power of, I don't know, let's just try 4. That is scientific notation in base 2, okay, because 1.011 is in base 2. Then you go like, okay, but what is the value being represented here? So this kind of ties into something that we worked on last Thursday. So we look at 1.011, and then we ask, okay, what value is 1.011 in base 2 representing? And the answer to that question is 1.011 in base 2 is 1 plus none of the halves plus 1 of the quarter plus 1 of the eighth. So this really boils down to 1.375 as a base 10 number. And then 2 to the power of 4 is 16. So now we have this. Oops, I keep doing this. I'm swiping it to to a new page unintentionally. So this is 1.375 times 16, and then the other way to do this calculation in an easier way is to look at this as 11 divided by 8 times 16, and then these two cancel out. We got a 2 left, so this really is just representing 22, okay, what we know as 22 in base 10. So do we have any questions about this particular conversion? Looking at a base 2 scientific notation and understanding what value it is representing. Okay, I'm not seeing any questions. Cool. All right. So without any questions, so now the only thing we need to know now is how many binary digits can we specify with the Mantissa. And once again, the Mantissa is this part here. In other words, 1 point, and then how many digits can we specify on the right hand side of the point. That can help us, that specifies the precision, okay, that can specify the precision of the Mantissa. And then the next question is, what range of value can we use for the exponent of 2? So that will give us the range of value that we can represent. So we have the precision, which is how many digits we can allocate to the Mantissa. And then we have the range, which is specified by the range of values that we can specify for the exponent in base 2 in this case. So those are the only thing that is kind of, depending on what format we are using, the range will be different, and then the precision would also be different. Alright, so I'm just gonna take a pause here and see if you guys have any questions. And then I can have a little bit more coffee. Alright, no questions. So without any questions, we are going to switch back to the browser. Okay. And there are a few links here. Okay, so this link here goes to the Wikipedia discussion of what is a double precision floating point number. So I'm just going to go there to take a quick look, because somebody actually spent the time to represent a floating point number in a color-coded fashion like this, which makes it kind of easy to understand. Oh, where does 11 divided by 8 come from? Okay, let's switch back to the tablet first, and then I'll explain that. Alright, so we have 1.011 in base 2, which is 1 plus 2. Oh, okay, let me start from the beginning. We have 2. Okay, even better. We have 1 times 2 to the power of 0 plus 0 times 2 to the power of -1 plus 1 times 2 to the power of -2 plus 1 times 2 to the power of -3. So this one is this one here, this 0 is this 0 here, and then this one is this one over here. And I keep switching to the next page, so I'm gonna have to disable that feature. Okay, so does that answer the question? Does that answer the question of where I got 11 divided by 8? And I got a bunch of people typing, so I'm gonna wait a little bit. This is the one downside. Well, actually, I wouldn't call it a downside, but this is the one of the adjustments I have to make, teaching a class. It's 1 and 3/8, yes, and therefore it is also known as 11/8. There we go. Excellent. All right. So now we get back to the Wikipedia page, and it is. Okay, come on. There we go. So it's color coded. We allocate 1 bit, okay, the sign bit, which is here. If the sign bit is a 1, the value being represented is negative. If the sign bit is a 0, then the value being represented is non-negative. So that's the one job of the sign bit. Okay, there's only 1 bit allocated for the sign. And then we have the green portion. The green portion has 11 bits. It specifies the exponent in a very strange way. So I'll explain why it is a little bit strange. And then we have the, I guess, salmon color portion, which is this portion here. There are 32 bits to it, which says fraction. It doesn't say Mantissa, it says fraction, because it is really the fraction of the Mantissa. Okay. And then the value being represented by a 64-bit double precision floating point number can either be expressed this way, or it can also be expressed this way. Okay, they are really the same thing. One uses the sigma notation, so that the value of the Mantissa is 1 plus. So you can see how this 1 is always there. It is not represented anywhere within the 64 bits of a double. Okay, so that 1, this 1, plus, or this 1 point, this 1 here, or this 1 here, it is always there. So the pink portion is only representing what is to the right hand side of the point, okay, being this point over here, or being this plus over here. So I'm not going to spend the time to talk about the index of I, how I goes from 1 to 32, and then we basically just end up looking at the pink portion as one gigantic value that is less than 1, specified by negative powers of 2. Okay, that's basically what it boils down to. The other representation is look at that portion as B51, B50, all the way down to B0. So the part that is a little bit awkward is the green part. Okay, the green part, which is our exponent. So if you look at the green part and use the unsigned, I repeat again, using the unsigned interpretation, it will give you a value called E. So E can basically go from 0 all the way to 2048, 47. And then you take that value, okay, and then you subtract 1023 from it. That becomes the actual power of 2 that you want to multiply to the Mantissa. All right, so this E is really just the unsigned interpretation of the green portion. That is a very good question. In this class, we don't use natural log at all. So almost, if I would say every single time we refer to E, it is just referring to the unsigned representation of the green part. Okay. So if it looks a little bit awkward and strange, we'll work out a few examples, and hopefully those examples will help us clarify some of the concepts. So now I intend to move to the new page. Go ahead, question? The dot is not represented. The dot is implied. The 1 is implied as well. So the 1 point is actually implied. This portion is always implied to be there. So we have 1 bit for sign. We have 52 bits for whatever digits is to the right hand side of the point, and then we have 11 bits for the E, and that is all. That accounts for the 64 bits already. So that leaves the 1 point always there, which raises a kind of interesting question, which is how do we represent 0? Because if you think about it, we cannot represent 0 if there's always a 1 point in the Mantissa. So we'll answer those questions later. Okay, so right now we're gonna look at a few examples. Go ahead. Okay, so we'll start with some value that we are familiar with. Okay, so we'll say let's try, I don't know, let's try 21.75. Okay, which is in base 10. Okay, oh, I have to switch to the tablet. There we go. So we're looking at a value of 21.75 exactly, and we want to use the double precision floating point number method to represent it using 64 bits. Okay, so how do we do this? Okay, that's the question. How do we do this? So the first thing you can do, there are several ways to do it. There's no single right way to do this. But one way to do it is to convert 21.75 into a binary representation first. So remember, when you're converting a value into binary representation, you're really just trying to use powers of 2, the presence or the absence of powers of 2, and then when you add up all of those powers of 2, you get as close as you can be, to a particular value. In this case, 21.75 in base 10. So we'll say, yep, we got a 16. We don't have an 8 after the 16. We do have a 4. After the 4, we don't have a 2, and then we have a 1. Okay, so that accounts for the powers of 2 that are not fractions, okay, or the non-negative powers of 2. And then on the other side, we have a half and a quarter. Those are also powers of 2. So remember, just think in powers of 2, including negative powers of 2. And then your job is really just to try to figure out, where do I need 1 and which one I don't need at all. Okay. So now we have 1, and then we have none of the 8, 1 of the 4, none of the 2's, 1 of the 1's, and then point 1 half, and then 1 quarter. And this is the base 2 representation of exactly the same value that we know as 21.75. Do we have any questions about this conversion process? Okay. You can always apply the formula that I have put into the module in base conversion. That one, it converts 1 digit at a time, but it works in this case as well. Okay, you can convert it into base 2. So now we see this and go like, but tech, this is not it's not normalized, okay? Because we can see that it's not 1 point something something times 2 to the power something. So we'll do it one step at a time. So the first thing we do is to move this point just one place to we'll move the point one place to the left hand side. So it becomes 1010.111 in base 2. And then somebody's going to say, but that's not the same value anymore. How messy do the bits get when the end number isn't 5? Oh, it can get pretty messy. I mean, there are a lot of it's kind of like when you're converting between base 10 and base 3, that would be very messy most of the time. Okay, so but this is, we have to multiply this 2 by 2 in order to make up for moving the point. Alright, so we are not talking about the quiz from last Thursday. Let's kind of stay on focus right now. Yes. Well, no matter how accurate, certain values cannot be represented exactly. So we can we'll just exhaust all 52 bits for the fractional part of the Mantissa, and that's the best we can do. All right, so that should answer the last question. Okay, but let's go back to the whiteboard at this point. And now the question is, why do we have to multiply this by 2? That has to do with when we shift the point from here to here, we are actually dividing the value by 2. Now, for those of you who don't believe me, you can do it on the side. Okay, you can say, okay, I want to look at 1010.111 in base 2, and I want to know what value it is representing. Okay, so this is an 8 plus a 2 plus a half plus a quarter plus an eighth. Oops. And that turns out to be 10 point let's see, 875. Okay, in base 10. And I did it again. I keep moving to the next page. Maybe I can turn off something so it doesn't automatically do that. So I'm going to turn off swipe, and then we'll see. Alright, so when you compare 10.875 and 21.75, 10.875 is exactly 1/2 of this. Okay, so that means this value over here in base 2 is 1/2 of the value here in base 2. And that's why in order for the value being represented, which is exactly this value, to be preserved, I have to multiply it by 2 to make up for moving the binary point. You can always think of, there's always a power of 2, except initially it is 2 to the power of 0. Now we have 2 to the power of 1, and then we have 101.0111 in base 2. And this time it will be to compensate for moving the point 2 places to the left-hand side. Now we have 2 to the power of 2 to make up. And you can kind of see that if I want everything to be normalized, I end up with 1.0101 in base 2 times 2 to the power of 4. Because altogether, I have to move the binary point exactly 4 times to the left in order to end up with the Mantissa that is normalized. So this is the Mantissa. Okay, remember what I said earlier, the Mantissa is always between 1 and excluding 2 itself in base 2, so it can have its 1 point and then a whole bunch of digits. They can all be 1s, but the value of the Mantissa is always less than 2 because 2 is our base. And then we end up with an exponent here so that we can specify the actual scale that we need to multiply to the Mantissa here. So we got a question coming. I'll wait for that question and then answer the question, and then we can move on. So if you guys have any additional questions, use this opportunity to type up your questions. Alright, so the question is, but if we assume that there is always a +1, then can we do no? The answer is no, because that is not how the standard is specifying. The standard says the 1 point part is explicit. Is there an extra 1? You're correct. There is an extra 1 here. Thank you. That is correct. There is an extra 1. Almost. So the Mantissa is greater than or equal to 1, but it is less than the base, which is 2 in our example here. So it's between 1 and 2, excluding 2. All right. And then we got one more question coming. Or you erase a part of the 2, so I'm going to put it back here. All right. Okay, so, and then Chris said it's just like how in base 10 the first digit is always between 1 to 9. That is correct. So in base 10 the Mantissa would be between 1 and 10 but excluding 10. Cool. All right. So now the question is, okay, fine. Now that we can convert 21.75 in base 10 into a binary number that has a Mantissa that is normalized because it is between 1 and 2, excluding 2. And it also has an exponent of 2 specified over here to specify the scale that we want to multiply to the Mantissa. How is this represented? Well, let's go ahead and piece together all 64 bits, right? So we have a 0 for the sign bit because the value being represented, 21.75, is not negative. So the sign bit is a 0. And then the next thing we encounter right away is, what is E then? Okay, so E is the biased exponent. It's biased by 1023. Now don't ask me why it is biased by 1023, because if it were biased by 1024 it becomes the signed representation, which is great. But no, they decided not to use the signed representation. They decided to use an unsigned representation and then a bias. Don't ask me, because it's a decision that was made long ago by electrical engineers, not by computer scientists. So E in this case is going to be what we really want to be the exponent plus 1023. Once again, the 1023 is a bias. Okay, it is determined by the standard itself. I didn't come up with it. It just comes with the standard. Okay, so E becomes 1027. So 1027 is relatively easy to convert into base 2 because it's just 1024, which is 2 to the power of 10 plus 2 plus 1. Okay, so it's not too bad. Okay, so we have a 1 and then a whole bunch of zeros, and you can count the number of zeros because 1024 is 2 to the power of 10, which means if you just want to represent 1024, you will need a 1 and then 10 zeros after that. But we also have a 2 and a 1. That takes up the least significant 2 digits to be 1s. So that means we only have 8 zeros left to write. So we will count 1, 2, 3, 4, 5, 6, 7, 8. And then 2 1s over here because 1 is a 2 and then the other one is a 1. So now we have 1024 plus 2 plus 1, which is 1027. So this entire part here is E, which specifies the biased exponent. Okay, 4 is the actual exponent that we want, but IEEE says, but we don't want you to specify 4 here. We want you to specify a biased exponent here, which is what we really want, plus 1023. And here we go. Here, this is what we have. This portion here is the fractional part of the Mantissa. So we just copy and paste it into the double representation. So now we have 0, 1, 0, 1, 1, 1, and then the rest are all 0. So now we have this part here being the fractional part of the Mantissa. And how many zeros do we have with these dot dot dots? However many zeros we need to make up for 64 bits. And we got people typing. Excellent. So I'm gonna wait a little bit and finish up my coffee. Why are the trail? Well, because you can always add none of the smaller powers of 2 without changing the value that we want to represent, because they're always zeros. Okay, here right? You can append as many zeros as we want. That won't change the value of the mantissa. It seems wasteful. It's not wasteful because I just so happen to choose a value that is easy to represent using very few bits. But if you were to change 21.75 to just 21.74, it would take a lot more digits to do it. So it's not. It seems to be wasteful, but it's really not. No E. Not sure what that means. E seems wasteful. I'm not sure wasteful in what way. No, floating point is not always 64-bit. And there's a reason why this is called a double precision, right? I mean, if something is called double precision floating point number, you can probably guess there's a single precision. And a single precision is known as float in C. A double precision is known as double in C. And there's also a quad, a 128-bit version of this, that can specify higher precision and even a bigger range of values. All right. Yes. This is the interesting part about representation is representation doesn't say anything about efficiency. So a long time ago, there was a processor called the 8386 processor, and any processor before that does not have a built-in floating point number unit. And as a result, everything that you want to do with float or double, whether it's addition, subtraction, multiplication, and otherwise, they all have to be done using integer math, which is also why floating point and generally speaking, floating point number calculations are very inefficient back in those days. You can do this with an 8-bit processor. I mean, you can find that the Arduino has can use double, and it's only an 8-bit processor, right? I mean, so this can all be done using an 8-bit processor that is not capable of understanding floating point number representation itself. It's all done by libraries, which is highly inefficient. All right, so I'm looking at the text channel, and the first question is, how did you get that binary E? That is the biased representation of the exponent. The actual exponent that I want is 4, but then the bias is 1023, so 4 plus 1023 is 1024. And then the next one says, adding the 1023 seems wasteful. Extra bits. It's not wasteful because that is how we can potentially represent huge, gigantic values and also very, very small values. Then the next one is, why is there a leading zero on the fraction part? Alright, so we don't really have a leading zero. That zero is coming from here. So it's not exactly a leading zero because that zero is there because in the mantissa we do not want a half. So it is not a leading zero. Oh, it's not wasteful, it is limiting. Well, you can only allocate so many bits for the exponent. I mean, either way you want half of the exponent to be positive and the other half to be negative. So you're really trading off, usually by 1. Okay, are we ranging from negative 1024 to positive 1023, or are we ranging from negative 1023 to positive 1024? That really is the only question. And then we got one more person typing. There we go. We add the bias because it helps us represent negative and positive exponents. Yes, that was the intention. They could have used the signed representation too, but they did not. I suppose they only had hardware back in those days that can deal with unsigned representation. I don't know exactly why, but If they had used a bias of 1024, things would be a whole lot easier to deal with. But it's a minor point, it's not really that big of a deal. All right. Any other questions before we continue? All right. So now the question is, how can we check that Tech has got his math right? Okay. So the first thing we need to do is to look at the 64-bit in an easier way, okay? Because there's no way, well, there's no easy way for you to enter a constant in binary in C or C++. In GDB you can, okay? In GDB I think 0t as a prefix allows you to specify binary numbers. I think it's 0b as a prefix. I cannot remember, but there's a way to specify a binary number. But in regular C and C++ programs, you cannot do that. Okay. So what we do is we use hexadecimal. Okay. You guys remember hexadecimal? So we basically group things into chunks of 4. So we basically just say, okay, every 4 bits, is one chunk, and one chunk is officially a hexadecimal value. So now we got a 4, 0, 3, and then this is a 5, that is a C, and a whole bunch of zeros. So now in hexadecimal we have 4, 0, 3, 5, C. That specifies 5 digits. Okay, so how many digits do we need in hexadecimal to fill up 64 bits? One hexadecimal digit accounts for 4 bits, right? So when you do the subtraction and the division, we have 11 zeros to make up for the whole thing. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So Tech claims that the bit pattern specified by this hexadecimal number is going to represent the value of 21.75 in base 10. And you guys go like, I don't think so, right? I mean, it doesn't even look like it. So what do? Well, we test this out, okay? We write a program to test this. So now we can, okay, I lost my mouse pointer again. There we go. Alright, so we go to onlinegdb.com. This is really a useful website. So we switch to C, and we are going to go include stdint.h, standard integer.h. So this way I can designate the width of integers. And then the main doesn't really need to be fancy at all. So for main, okay, I pressed the wrong key, sorry about that. I just need a local variable, which is uint64 underscore t. We'll call it x. And I'm going to have one kind of stupid statement here to initialize x to 0, because otherwise the compiler would actually optimize the existence of the local variable, which then means I cannot do what I want to do. So x equals to 0 is necessary just to shut up the optimizer and go like, no, do not optimize the existence of x out of this program. And then to put a single breakpoint here. And then you guys look at this program and go like, hey, this program has no mentioning of double. It has no mentioning of the constant that we just talked about, in the tablet. It certainly has no mentioning of 21.75 in it either. So how is this going to help us, right? Well, I'll show you guys how it's going to help us. So we go to debug, and everything is going to be in the debug. So I'm going to bump up the portion of debug, and you kind of get rid of most of the other stuff. And we'll run the program, because we already set up a breakpoint on line 16. So when we run the program, it will pause on line 16, just like that. So, and then we print x is 0, no big deal. Okay, so now what do we do, right? So now we say set var x equals 2, and then I'm just copying from the tablet. Okay, you guys cannot see it, but since I have the tablet as an actual device, I can see it on my side. But it's really the same number. Okay, 4, 0, 35C, and then 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. Press the enter key, and now we print X again. That doesn't look like 21.75, not even close. And some people would say, maybe you should cast it. Nope, that doesn't help at all, right? So when we cast it, it just gives us, 4.6 something, E plus 18. In other words, it's just printing it in scientific notation, but it's not really giving us the value that we want. Well, the reason why it's not working is because casting is preserving the value. In other words, if X is, 4.6 times 10 to the power of 18 or something like that, casting it to a double is preserving the value, just changing the type, to something else. Okay, so that's not going to help. So what I want to ask you now, step by step, is to ask, what is this? I'm not sure whether you guys can see it on your screen or not. I don't know whether there's a way to bump up the font size. Does everybody see, what I have printed here? You can see? Okay, excellent. Logical? Oh, it's legible. Okay, excellent. Cool. So now the question is, what is that? What is ampersand X? This is the address of X. Okay, close. Okay, so in C and C++, we actually have address of instead of reference of. In Java, we use reference of. In most scripting languages, we use reference of. But in C and C++, we actually have the address of. Okay, very good. And what is the type of ampersand X? Knowing that X is a 64-bit unsigned integer, this would be the address of a uint64 underscore t, right? So, okay, no big deal. So what I'll do is I'm going to typecast the address. So I'm typecasting the address of X. I'm not typecasting the value of X. Okay, this is a very important step. So I use double star to cast the address of X. In other words, I'm basically telling the debugger and say, hey, go to that location, go to the starting point of where X is in memory, but don't treat those bytes as components of a 64-bit unsigned integer. Instead, treat those 8 bytes as a double. But it is still an address, right? So if I press the enter key right now, it would just give me the address, okay? So it's not helping me that much. On the other hand, if I put one more asterisk on the left-hand side, now I'm saying, now that we pretend that those 8 bytes are the bit pattern of a double, tell me what is the value at that address. So now the debugger is interpreting those 8 bytes or 64 bits using the double format standard. Okay, and this is the moment of truth. Okay, are we going to get 21.75 back? Yeah, yes, right? And we get it back. So this is an interesting experiment, right? Because we are using very simple C operators in order to demonstrate how we can put a certain bit pattern into memory, pretending that it is just an unsigned 64-bit integer, and then we can ask the debugger to interpret the very same 64 bits using the double precision floating point number method, and now the value is 21.75. So we got a few questions coming. All right, excellent. Maybe not. I thought I saw someone typing. But do we have any questions? Now would be a good time to ask if you have any questions, because we just went through some major conceptual tricks to get this to work. Okay. All right. So we got a few questions. Why does it say ampersand XLE? XLE. I don't see XLE. I see ampersand X. Oh, okay, I see. Right here. Okay. I think that is. I think that's left over from. Yeah, I think it's just left over from the dumb terminal emulation. It did not quite clear the previous screen correctly, or something like that. And then Omar says the module says bit 43 is different from the MSB in signed integers. So it's different in the way that the sign bit in a double is really just the sign bit itself. It doesn't use the 2's complement method of representing negative values. So I hope that answers Omar's question. Yeah, so let me just repeat what I said. The signed values in double does not make use of 2's complement. The sign bit is really just, indicating the direction of the rest of the number. Yep, it really is just a flag. Yep, exactly. All right. Any other questions? Oh, okay, here we go. How do we represent 0? That's a good one. So 0 is represented by making all the bits 0. In other words, what we should have as the smallest possible value representable using a double, we fudge it and say that really is 0. That's the answer. And double is interesting. It can also represent not a number, nan, N-A-N. It can also represent positive and negative infinity. So there are specific bit patterns for representing positive infinity, negative infinity, not a number, positive not a number, negative not a number, and 0. Those are very special cases of the bit patterns. We sacrifice certain actual legitimate values to represent those, kind of special values. But not the 1. Not really sure what that question is. It can represent 1 as a value, but it can, if without treating a special case as 0, there's no way to represent 0. Exactly. So Andrew is correct. Okay, so let's see how 1 is represented, okay? Because I think that's another good exercise that we can do. And now when I need to swipe to a new page, it won't let me open a new page because I turned it off. So I now have to turn swipe back on, switch to a new page, and then turn it back off. There we go. Alright. Alright, so let's see how we can represent the value of 1. Okay? So we look at 1 and say, oh, that's easy, because 1 is just 1 point, blah, 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 times 2 to the power of 0. Oh, okay, we're done. Okay, we have the Mantissa, because now the Mantissa is greater than or equal to 1, less than 2. We're done. Okay, so now we say, so basically the fractional part of the Mantissa would be just a bunch of zeros, right? There's just a whole bunch of zeros over here. And E is the biased exponent. The actual exponent that we want is a 0. So the biased version of that is just 0 plus 1023, which is just 1023. So now when we look at the overall representation, it is 0 for the sign, and then for the exponent, it is 1023. So we have a 0, and then followed by 10 ones. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this portion here is E, which is the biased exponent. And I got some questions in the text channel. The 0 before the x is not part of the value. It is just a notation. That is correct. So 0x together is the prefix of a base 16 number. I thought that was taught in CISP360. Apparently that is not the case. Okay, so I apologize for the assumption. 0x is considered as a prefix for a base 16 or hexadecimal number. Okay, getting back to here. And then the rest, which is the fractional part of the Mantissa, they're all zeros. Okay, this is the fractional part of the Mantissa. So now, when we look at this from the perspective of hexadecimal representation, we have a 3, we got an F, we got another F here, and then we got a whole bunch of zeros down there. So we have 3FF followed by 13 zeros. Okay, so we want to see if that is the case, right? Oh, okay, I just got out of the debug mode. Let's go back into debug mode. Alright, so this time we're going to do it the opposite way, okay? Oh, okay. Okay, so Rachel said for representing 0, it would be 1x 0. Basically, we look at the smallest possible value and then we treat it as if it is 0. But let's follow up, let's finish this sample program first, see how 1 is represented, and then we'll look and see how 0 is represented. Because altogether we need to make up for 16 digits. So if I specify 3, then the other 13 digits would be zeros to make up for 16 hexadecimal digits, because one hexadecimal digit accounts for 4 bits. Okay. Yes, I did ask how to represent 0, and there's no way to truly represent 0. We basically consider a certain bit pattern as, and we interpret the bit pattern of all zeros to be representing 0, when it really is representing the smallest possible value that we can specify in a double representation. So it's a special case. 0 is a special case. Okay, so I can do a few experiments here. So let me in the debugger, let me just kind of run up to the breakpoint. So this time I'm gonna do a set var again, but this time it's gonna be exactly the opposite. So let's take a look at 0 first. Okay, so what we do is we dereference the typecasted address of x and say I want to store 0 over there. The Mantissa, we cannot specify a Mantissa of 0 because the 1 point is always there, and that's why there's officially, if you follow the rules, if you only use the interpretation that we have talked up to this point, there's no way to represent an actual 0 as a double. So what they do is they look at the smallest possible value you can specify in the double representation that we are talking about, and they just fudge it and say that is not the smallest possible value, that really is 0 itself. And that is how we represent the value of 0. Which I know is really weird. But what we want to do, okay, so I'm going back to the debugger right now. I am basically storing the value of 0 as a double. And then we want to look at the hexadecimal representation in x, and we can see that it's just a whole bunch of 0, okay, because it is a special case. Not everything. 0 is a lie, positive infinity is a lie, negative infinity is a lie, positive not a number is a lie, negative not a number is a lie, but everything else is not. All right, so now we want to look at 1, okay, because remember, this is what we were working on, how 1 is represented. And now we look at the hexadecimal representation of x, and we get 3FF and then followed by 13 zeros. So that confirms what we observed earlier. They are not lies. Okay, technically, Zoe, they are not lies. I would call these exception to the truth. Exception to the truth. There we go. Yes, Chris, you are correct. So the value that otherwise would be interpreted as 1 times 2 to the power of negative 1023 is fudged to be representing 0 exactly. And there's no real easy way to explain this, other than to say that, no, they just chose a representation to represent 0 because there's no actual way to represent 0. There we go. So for those of you who are kind of obsessed about this, you can go to the Wikipedia page, and they will talk about all the special representations. Let's see here. There are. I'm just looking at the special ones right here. Exponent encoding. Okay, that's something that we talked about already. I'm just looking at how 0 is represented. So they gave you a whole bunch of representations too. So there's a positive 0 and a negative 0 because the sign bit is just indicating which way the value is going. So if the value is 0, we end up with 2 possible zeros. We have a positive 0 and also a negative 0. And then it says the encodings of not a number. And then there's also infinity too. So I know there's an infinity representation. So anyway. Yes, we are making the rules. Yep, exactly. They are not alternative facts if everybody is going by the same facts. You can make your own processor that doesn't play by these rules. There we go. Okay. Alright, so Omar says, does it make a difference whether exponent adds or subtract 1023? So whatever those 11-bit is representing as an unsigned number, you have to subtract 1023 to get to the actual exponent of 2 that we want. We are adding 1023 so that we end up with the biased exponent. I didn't use e plus 1023. I had 4 plus 1023 equals to e. So e is still representing the actual biased exponent, but you add 4 to 1023 because 4 is the actual exponent that we want. All right. Just looking at the time and continuing to answer questions in the text channel. And meanwhile, switching back to my notes here, and hopefully we have time to go through this mess over here. Isn't that what machine epsilon is? I'm not familiar with the concept of what is a machine epsilon. You mean the smallest quantum that can be discerned by 2 adjacent values? Yeah. Oh, okay, I see. Well, that epsilon changes too, depending on the exponent. Because in the end, what is specifying the precision, of how well we can represent a value is the number of bits that we allocate to the fractional part of the mantissa. Those 52 bits is what determines how accurately we can represent a value. The exponent is really a scaling factor, so it's just specifying which power of 2 should we multiply the mantissa with in order to get the value that we really want to represent. All right. So with the next 20 minutes, 10 minutes. Actually, we only got 10 minutes left. So with the next 10 minutes, I'm going to talk a little bit about how we use regular expression to specify a base 10 scientific notation. Yes, so we are switching gear a little bit here, and I have no idea why we have all of these color coding here. That was not in my original LaTeX format, but it is here because of how it's rendered. And that is not even close to the original mathematical notation. So anyway, so obviously they kind of, I mean, the rendering thing kind of messed up this portion a little bit. I think it misinterpreted some of the escape sequences as LaTeX when it's not actually LaTeX. It's okay, doesn't really matter. It is not colored in the website. Well, it is colored here. It must be a browser thing because it might be how MathJax is rendering depending on your browser. Anyway, so we'll go ahead and take a look at this thing here. Okay, so that looks good, and that actually looks better than what I have. So Chrome does the correct rendering in this case, and Firefox did not. Okay. Because some of the backslash open paren is missing from here, and that's why we have a little bit of an issue. I'm not sure whether I can turn that off or not, because backslash open paren is interpreted as the beginning of a math equation in LaTeX. So I think that is why we got the confusion. And we see two screenshots in the text channel. The first one is the intended output. The second one is what I am seeing on mine. So the first one is the correct one. All right. So instead of confusing you guys any further, I'll just say that forget about this part because I got this logic done already. Okay. So your after the exam, let me see. Okay, after the exam 1, okay, we're going to have a homework assignment. If I give you a base 10 scientific notation, I want a program to convert the value of the base 10 scientific notation to a double representation, or kind of close to a double notation. It's not going to be exact, but it's going to be close, okay? And then the idea of doing the conversion is you can basically count on I'm implementing the logic already to do this. Okay, so let's focus on negative 2.667 e negative 6. Okay, and my program is doing some conversion for you so that you don't have to deal with it. Okay, so I'm writing this on the tablet right now, and then we'll talk about what my program will do already and what you need to do in your part of the code. It is not tonight's lab, okay? Tonight's lab is a continuation of all the exponent crazy math stuff from last Thursday. So there'll be more crazy stuff like that tonight. All right, so getting back to the representation. So what my program would do is to say the sign is negative, okay? So it would be -1. And then it will look at the mantissa and it will say the mantissa is 267. But in order to use a mantissa of 267, it would also adjust the exponent in base 10 this time to, let's see. Okay, here's a quiz for you guys. What should I use as the base 10 exponent over here, because I changed the point from here to all the way over here? In other words, the mantissa is now 100 times what it should be. So how do I compensate with the exponent of 10? It's not -4. Go the other way. Alright, we got several people typing. That's what Discord is saying. Yep, you have to decrease it by 2. If it's -6 to begin with, decreasing it by 2 means it becomes -8. That is correct. Alright, very good. Okay, so my program, I have a subroutine to do this already. So my subroutine will indicate, the sign is a 1, basically. It will give you a initial mantissa as 267. Yes, I did say that mantissa is not supposed to exceed 10, or at least 10 in this case, because it's a base 10 number. But we'll look at this as quote unquote the mantissa. Okay, so fine. We'll be technical now. We'll use double quotes around mantissa because it's technically not the mantissa. So anyhow, but then it will also have a -8 as exp10. So the value that we are representing is basically -1 to the power of the sign times whatever the mantissa is, and this time we remove the restriction of the mantissa needs to be between 1 and 10 for base 10, and then 1 and 2 in base 2. So we'll just say the mantissa can be anything that we want it to be, okay? And then times 10 to the power of exp10, which is the exponent of 10, and we also have a 2 exponent of 2, which is represented by exp2. So exp2 is initially 0. Okay? So exp2 is initially 0, and you can see that exp10 in this case is -8. So now the question is, what do I need to do so that exp10 becomes 0? But I also want to preserve the value being represented as much as possible. That becomes the next topic. There's no way I can finish that topic in the next 3 minutes. It's going to take 2 labs to do this. Okay, so it's going to take 2 labs after the, well, we still have Thursday. So we can do this lab on Thursday, the first one. So the first lab is on Thursday. It's going to do in about a week. There is a lab tonight. The lab tonight is a continuation of all the exponent math, crazy math from last Thursday. The program is making the program. No, I will supply certain subroutines to make your job easier. So the homework is not to do everything yourself. It'll be somewhat guided when we get to it. So don't worry about it until we actually get to it. Okay. Let's see. The practice test is 2 days from today, which is the 18th, plus 7 is 25. Yes. So the 25th is our exam 1. Nope, the lab is not released yet. So I'm going to do it now. Let's see. Alright, so we have, this is our floating point 2 as a lab. And as we scroll through, you can see what the passcode is. So the passcode is EXP right there. There we go. And somebody, yep, there we go. Aaron just beat me to Discord text. So that's our passcode, and I'll give you guys the rest of, I'll give you guys the lab time to do it. Okay, I now know how to say things carefully. And today is the 16th, and the time is going to be 9:50 p.m. Pacific Standard Time. There we go. The exam time is correct. It is 5:30 to 6:50 p.m. on the 25th Pacific Standard Time. Alright, save and publish, and you should be able to start on tonight's lab now. There we have it. So I'm ending tonight's lecture 30 seconds earlier. Yes, you can complain to the dean and say, but Tech ended his class 30 seconds earlier. I want my refund right now. Alright, so I will talk more about the arrangement for exam 1 on Thursday, but right now, for the next 2 days or so, just kind of go over the practice test. Try to answer those questions as much as you can, and then I'll talk about how to solve the ones that you feel a little bit more challenging. Alright. Okay, so we're done for tonight's lecture, and I'm gonna stop all the streaming. I'll go away for maybe about 10 minutes, and then I'll be back to answer questions. Alright. So I'm gonna terminate all the